So what we have here is some applied examples. So this is for a chance for you now to check your understanding of going from an ordered differential equation, undertaking the Laplace transformation that you saw in part 2 of 3, and then finally, as you saw in part 3 of 4, where you algebraically manipulate the equation to end up in the transfer function form. These questions though, for the RC circuit and for the mass spring damper, are a little bit more difficult than the example we ran through because they contain obviously specific variables for the given system, so they're a little bit more difficult. So what you do have is the solution though for each one of the questions, because you've obviously got the transfer function here for the mass spring damper, which is the solution, and the transfer function here for the RC circuit, and also the pictorial form here. So have a go at that, so convert it into transfer function form and also sketching the diagram. I will provide a full work solution, so a video solution for the steps that I went through from getting from the ordered differential equation to the transfer function. I'll also do that for the next two further examples you've got. So for the water tank model here, and you can see here the corresponding transfer function. So converting from the ODE to the transfer function, and then from the DC motor here, and then converting here into, or if I go here, into the transfer function form, which obviously these are both represented as in previously you saw represented in pictorial form, block diagram pictorial form, as you can see here, and obviously here within the green box, where obviously the input is in this case flow in, output is the height, input for the DC motor is voltage in, and the output is the angle in this case. So have a go at those questions. I think they'll be very, very useful just to check your understanding of undertaking this kind of process. And you can just see the DC motor there spinning. So in summary, the benefits of moving from the time domain, so ordered differential equations, to the frequency domain or the complex frequency domain of Laplace have been given. So you've been able to see that we can effectively go from this ordered differential equation, undertake the Laplace transformation, you saw in video 2 of 4, and then algebraically manipulate the equation, because it effectively, when you convert into Laplace, you can treat the input, in this case F of S force, and the output displacement and the model here as three separate entities. So what Laplace then enables you to do is to algebraically manipulate the equation. And then what we can do is obviously represent it in block diagram form that you saw from the previous two examples that I showed you. So the mathematical process has been shown for this. I've gone through one worked example through the 4 videos, and then you've got the 4 further examples to have a go at. So the applied examples for you to have a go at, the exercises. And as I said, I will provide full work solutions for them to reinforce your learning of going from the ODE to the transfer function. And it's been demonstrated how effectively a component, in this case we've been focusing primarily on actuator and process, but these form part of the closed loop control system, and these can be represented via the use of a mathematical model. So we could represent, I don't know, the dynamics in terms of the height of the tank changing, the dynamics of a DC motor, the dynamics of a mass spring damper, etc. So I hope this video has been useful, and the series of videos have been useful, and it's enabled you to learn and understand how to go from an ODE into a transfer function, and also some of the reasons and the benefits as to why we do this. And some of the benefits won't become entirely clear in this video, but they will become clear as you work your way through more and more of the kind of the control theory beyond that of transfer functions. So you'll understand the kind of the significance of a particular transfer function. Right, so thank you for listening. I'll speak to you soon.